Hello students, this is the subject Business Statistics second paper for TY BCom students. We are starting with second term syllabus now. This is Unit 5, Lecture 1. Name of the topic is Normal Distribution. Normal distribution, definition, properties of normal distribution, and we are going to see examples and problems based on normal distribution. Second term syllabus for TY BCom students. Subject name is Business Statistics second paper. Unit 5, Normal Distribution. There are 14 lectures allocated to this topic. See the syllabus for this term. Normal distribution, definition, probability density function, curve, properties of normal distribution, state, mean and variance, standard normal variate, problems to evaluate probabilities using statistical table and Excel, additive property for two variables, statement only, fitting of normal distribution using Excel, examples and problems. So let us see some introductory part for normal distribution. Normal distribution introduction. Normal distribution or Gaussian probability distribution is one of the most commonly used distribution. It is important due to wide use. The variables such as intelligence quotient, height of a person, weight of person, errors in measurement of physical quantities follow normal distribution. Normal distribution is useful in statistical quality control. Normal distribution is useful in statistical quality control, statistical inference, reliability theory, operation research, educational and psychological statistics. In the theory of sampling, design of experiments also, normal distribution is very much useful. Normal distribution is viewed as a limiting distribution of several distributions such as binomial Poisson. See the definition of normal distribution. A continuous random variable x is said to follow normal distribution with parameters mu and sigma square if its probability density function is given by fx is equal to 1 upon sigma root 2 pi e raised to minus 1 by 2 x minus mu upon sigma whole square. Range of x is minus infinity less than x less than infinity, minus infinity less than mu less than infinity, sigma is greater than 0 and equal to 0 otherwise. See the properties of normal distribution. First of all, we will see the notation. X follows normal distribution with parameters mu and sigma square, where mu and sigma square are the parameters. Mu is equal to mean and sigma square is equal to variance. If mu is equal to 0 and sigma square is equal to 1, then the normal variable is called as standard normal variable, that is normal 0, 1. Generally, it is denoted by z. The probability density function of z is given by f of z is equal to 1 upon root 2 pi e raised to minus 1 by 2 x minus mu upon sigma whole square, minus infinity less than z less than infinity. Third property, the probability density curve of normal mu sigma square is bell-shaped, symmetric about mu and mesochrotic. Naturally, the curve of standard normal distribution is symmetric around 0. So this is our probability density curve. This is asymptotic to x-axis. It will come closer to x-axis, but it will never touch x-axis. Fourth property, as the curve, it should be curve, CURV. As the curve is symmetric about mu, the mean, median and mode coincide and all are equal to mu. So for normal distribution, mean is equal to median is equal to mode is equal to mu. Now computation of probabilities. If fx is a probability density function of x, then probability a less than x less than b is equal to integral a to b fx dx. It is equivalent to the area under the curve fx bounded by x-axis, and the ordinates x is equal to a and x is equal to b. If x follows normal with mu sigma square, then z is equal to x minus mu upon sigma follows normal 0, 1. So x follows normal mu sigma square, then probability x greater than a is equal to a to infinity 1 upon sigma root 2 pi e raised to minus 1 by 2 x minus mu upon sigma whole square dx. The above integral cannot be evaluated directly by using usual techniques. The values of integral are tabulated for a greater than 0 only for standard normal variable. The table is referred to as normal probability integral table. This table is called as normal probability integral table. In this table, the values, the column numbers are starting with 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9, and row numbers are 0, 0, 0.1, 0.2, 0.3, 0.4 up to 4.9. See some specific things we have to remember in this particular table. If you observe 1.29, the value is in bold. See 1.28, the value is 10027, and after that the value is 98525. So this value is printed in bold letters. So this 0.0 should be preceded with this value. So we can read this value as 0.098525. So 1.3, the value 1.30, the value can be read as 0.096800. So this way, if you observe 2.3, third column, 2.33, again it is in bold, it is printed in bold letters. So definitely these two zeros should be preceded from these values. So this value 2.43 ordinate, then the probability can be read as 0.0099031. Same is the case with all other values. Wherever you have getting the bold letters, the zero should be preceded from that particular value. Okay, so this is the way we can read the normal probability integral table. Now we will see some properties of normal distribution again. See, thus to evaluate probability x greater than a is equal to a to infinity 1 upon sigma root 2 pi e raised to minus 1 by 2 x minus mu upon sigma square dx. We need to convert it in terms of normal 0, 1 by using the transformation z is equal to x minus mu upon sigma. In order to obtain the probability of any region, we use the following rules. First rule, the total area under the probability density curve is 1, that is minus infinity to infinity fx dx is equal to 1. Second rule, the probability density function curve of normal 0, 1 is symmetric about 0. Therefore, if we fold the curve about y-axis, that is at x is equal to 0, the two parts coincide. Thus, we get area of right tail and that of symmetric left tail same. In other words, for z following normal 0, 1, probability z greater than a is equal to probability z less than minus a. This type of region is called as probability z greater than or equal to a, and this marked portion is the tail part of the curve. So we can get the answer directly from the table. So probability z greater than or equal to a is equal to table value. Then probability z less than a less than minus a and probability z greater than a, the area will be same. Next rule, area below the ordinate is equal to 1 minus area above the ordinate. So probability z less than a is equal to 1 minus probability z greater than or equal to a. So we can say that is equal to 1 minus table value. Fourth rule, if x follows normal with mu sigma square and suppose we want to find probability x greater than or equal to a, then we transform the variable x to z, a normal 0 1 variable, and obtain the probability as follows. So probability x greater than or equal to a is equal to probability x minus mu upon sigma greater than or equal to a minus mu upon sigma. So we can write this as probability z greater than or equal to a minus mu upon sigma which is equal to table value. The following example will give clear idea as how the normal probabilities are computed using the tabulated values. See the example. Let x follows normal with 3, 4. That is mean is 3 and variance is 4. Find first part of the problem, probability x greater than 5. Second part of the problem, probability x less than 1. Third part of the problem, probability x greater than 0. Fourth part of the problem, probability x less than 6. Fifth part of the problem, probability 2 less than x less than 6. Sixth part of the problem, probability 4 less than x less than 6. So this is the problem. Now we will see the solution. We know that if x follows normal with mu sigma square, then z is equal to x minus mu upon sigma follows normal 0 1. So in this example, x follows normal distribution with mean 3 and variance 4. So then mu is equal to 3 and sigma square is equal to 4. Therefore we can say sigma is equal to 2. Therefore x follows normal with 3 4. Then z is equal to x minus 3 upon 2 will follow normal 0 1. We need to express first of all probabilities in terms of standard normal variable z. So first part of the problem, probability x greater than 5 is equal to probability x minus mu upon sigma greater than 5 minus 3 upon 2. So we can write this as probability z greater than 1.00. So if you observe this value, first of all we'll draw the normal probability curve. So it is symmetric curve, and this is left part of the curve, negative part of the curve, this is positive part of the curve. So positive 1.00 will come on positive side and we want greater part, so we'll mark the portion, right hand side portion. Now we will see how to see the value from the table. See the previous table. So 1.00 column, the value is, see 1.00 column, the value is 15866. It should be preceded by 0 point. So 0.15866. So this is the first answer we are getting. So the answer is there is equal to 0.15866. From normal probability integral table, we get the area of shaded region as probability z greater than 1.00 is equal to 0.15866. Then next part of the problem, probability x less than 1 is equal to probability x minus mu upon sigma less than 1 minus 3 upon 2. So we can write this as probability z less than 1 So which is exactly same as probability z greater than 1. So we will draw the curve and we'll mark the portion. The ordinate is negative. So minus 1.00 will come on negative side of the curve. And we want less part, therefore we will mark the portion which is left to the ordinate and which is same as probability z greater than 1. Just now we have seen that the value is 0.15866 from the table. Third part of the problem, probability x greater than 0 is equal to probability x minus mu upon sigma greater than 0 minus 3 upon 2. So probability z greater than minus 1.5. So minus 1.5 will come on left hand side and we want greater part, so we'll mark the right hand side portion. We know that if I see 1.5 in the 0 column, I am going to get the tail part of the curve. So 1.5 in the 0 column, the value is 0.066087. So, but we want the right hand side portion. So we know that the total area is 1. So this can be written as 1 minus 0.066087. So the answer is 0.933913. Next part of the problem, probability x less than 6 can be considered as probability x minus mu upon sigma less than 6 minus 3 upon 2. So probability z less than positive 1.50. Now again positive 1.50 will come on right hand side, positive ordinate, and we want less part. So we will mark the left hand side portion. But the value which I am going to get for 1.0 in the 1.5 in the 0 column is the tail part of the curve. So this area is nothing but 0.066807, which I don't want. So I want the left hand side portion and I can get the answer as 1 minus 0.066807. So the final answer is 0.933913. So both the answers are same. Fifth part of the problem, probability 2 less than z less than 6. It should not be z, it should be x. 2 less than x less than 6 can be considered as probability 2 minus 3 upon 2 less than x minus mu upon sigma less than 6 minus 3 upon 2. So we can write this as probability minus 0.5 less than z less than 1.5. So draw the curve. Minus 0.5 will come on left hand side, and we know that if I see 0.5 in the 0 column, the probability which I am going to get is nothing but the tail part. So this part is 0.30854 and 1.5 in the 0 column, the value is 0.066807. Both the values I don't want. I want the middle part of the problem portion. So I can write probability minus 0.5 less than z less than 1.5 can be considered as 1 minus 0.30854 plus 0.066807. So the total of these two values we will subtract from 1. So final answer is 0.625373. Then next part of the problem, probability 4 less than x less than 6. In this case, I am going to get probability 4 minus 3 upon 2 less than z less than 1.5. Only difference is that in the previous case it was minus 0.5. In the next part, I am going to get positive 0.5 and positive 1.5. So in this case, if you observe 0.5, the probability which I am going to get is nothing but it will cover 1.5 probability also, because this part is also covered from in the probability 0.5. So in such type of situations, from the 0.5 probability, I will subtract 1.5 probability. So 0.30854 minus 0.066807. So the answer is 0.241533.